All right, so before the long weekend, we were focused primarily on these two things, on Hooke's law. Okay, Hooke's law, remember, is that the restoring force, which varies linearly with displacement in simple harmonic motion, is equal to negative k times x, where k is the spring constant in newtons per meter, and x is the displacement from its resting position or equilibrium position. Okay? The situations we said we could encounter with Hooke's law would be if the mass on a spring is oscillating back and forth on a frictionless horizontal surface, okay, that would be the only force, and thus the net force. Okay? So sometimes Hooke's law, okay, or the restoring force is the net force. Okay? A question where that's the case might ask you for the acceleration of the object at a certain position, or give you the acceleration of the object at a certain position and ask you what the spring constant would be. Okay? Essentially, it looks like this. Okay? For something oscillating with simple harmonic motion in an isolated system, the restoring force is the net force, and they would be set equal to each other. Right? The other situation we talked about with Hooke's law was Hooke's actual experiment with the masses hanging from springs from the ceiling. Okay? In that case, the force in the spring would be equal to the force of gravity. Okay? Or the weight that was placed on the end of the spring. Okay? So that would be a negative k times x equals m times g situation. Hooke's law never gets more complicated than that. Okay? It's either going to be the net force or it's going to be equal to the force of gravity, and that's really about it. Okay, is that ringing the bell for Hooke's law? And then we talked about conservation of mechanical energy. Okay? We said that in a pendulum, okay, that we would have, obviously, EI equals EF, as we would in any conservation of energy question. Okay? But in a pendulum, our potential energy is gravitational. Okay, so we would have, nearing the end point of this, exactly the same setup as a roller coaster question. Okay? Things that would be different from a roller coaster question would be terminology that would be used. Right? We might get the word maximum amplitude. Okay? At a pendulum's maximum amplitude, what kind of energy does it have? Okay. This is the equilibrium position. Okay? There and there would be the maximum amplitude. So when a pendulum swings back and forth, how fast is it going at those positions? What kind of energy does it have if it's not moving at those positions? Potential only. That would be where it's highest above its equilibrium position and would have only gravitational potential energy. What kind of energy does it have at equilibrium? Kinetic. Okay, because that's where it would be moving the fastest. Right? And anywhere in between, it would have a little of both. All right, the other situation we talked about was the mass on a spring. Okay, still an EI equals EF situation, What's different is, okay, that EP is now elastic. Right? And that means using this formula. Okay? The elastic potential energy formula is derived from Hooke's law. Okay? Remember that work is average force times distance. Okay? So that means 1/2 of the maximum force, K times X again, okay, gives us 1/2 kx squared, okay, our potential elastic energy. Okay, so if we were looking at the end point of one of those, okay, EI equals EF, that would be 1/2 kx squared, AXI, sorry, okay, plus 1/2 mvi squared equals 1/2 kxf squared plus 1/2 mvf squared. Okay, same thing applies to this as would apply in a pendulum. You might get terminology like equilibrium position, maximum amplitude, okay, things like that. Would the same principles be true for the mass on a spring as for the pendulum? And what I mean by that is, what kind of energy would it have at its maximum amplitude? Mass on a spring going back and forth. When it's completely compressed the spring as far as it will go, how fast is it moving? 0. So at its maximum amplitude, either compressed or stretched, it has no kinetic, so it's all potential. And at equilibrium, it's all kinetic. Okay? Those same principles apply. Right? Is that ringing a bell? I'm only reviewing that because it's been a few days since we did any of it. Okay? So now, here's what I want to work on. Okay? We did these questions the other day, 3, 5, 7, 9, and 10. Okay? If you finish those, great. Work on the ones below. Okay? If you didn't finish those, I still want those ones done for practice. Okay? But what we're going to do is focus on these ones here, which are about Hooke's law, conservation of energy. Okay? I want to make sure we're really good at those before I give you an assignment with marks tomorrow, okay, on that material. All right? So if you have questions while you're working on this stuff, ask, and we'll go through it as a class on the board. Okay? That's the point of today. So coach practice. Okay? Let's make sure we understand this stuff. All right, so 4, 6, 8, 11, 12, 13, 14, 15, 16, okay? Working on those. Some of those, like, it kind of becomes more complex and then it actually falls off and is less complex as you go, okay? But you'll be able to handle it, no problem, okay? Ask for any ones that give you trouble so we can go through them together. All right, so we'll have a look at 8 here first, guys. So in this question here, we are given the mass, right? So we know that the mass is 0.40 kilograms, okay? And it's on the end of a horizontal spring on a frictionless surface, so isolated system here, okay? Reaching a maximum speed of 0.50 meters per second. All right, so I'm just gonna write that that's actually the maximum as part of my givens here. Okay. Why is it important that I know that's the maximum speed? Where does that occur? At equilibrium. Okay, so I know that if that's my maximum speed, that's also the maximum kinetic energy the object's going to have. All right, so I might actually make that my initial point. Okay, then they tell me the maximum displacement of the mass is 0.11 meters. Okay, maximum displacement is also known as amplitude. Right, so I'm going to write an A there, 0.11 meters. We're looking for K. All right, so here's the key thing that helps you solve this question. I am told information about the equilibrium position and about the maximum amplitude. The energies at those two spots are numerically equal, but they're different kinds. At the maximum speed, which occurs at equilibrium, we only have kinetic energy because the displacement is 0 at equilibrium. And at the maximum displacement, we only have potential energy because that's where it stops, turns around and goes back towards equilibrium again. Okay, so if we know those pieces of information, the only thing we don't have is K. So we can cancel the halves, divide both sides by A squared, and we're solving for K. So if we punch our stuff in here, so 0.4 times 0.5 squared, okay, divided by 0.11 squared, okay, 8.3 newtons per meter. Okay, everybody all right with that? Lots of questions go like that. In fact, I put a question like that on the unit exam before. Okay, like it actually tricks people because they think, oh, Codere wouldn't give me one that easy. Okay, because it seems like, oh, I should have to do more for a question like that, but you don't. What it's testing is, can you read that question and know which two positions I'm talking about? Okay? I know you can do conservation of energy questions. You've been doing them since Science 10. This is more of a, do you understand what kind of energy is at each of those positions? That's more valuable to me on an exam when I'm testing. Okay? All right, sorry, okay, 12, right? 14. 14. Okay. All right, so objects on the end of a horizontal spring, we're given K. Okay, maximum speed, okay, is 0.35 meters per second. Maximum displacement, okay, 0.29. Okay, what's the speed of the object when its displacement is 0.1 meters? Okay, so that would be another x. Okay, and they want to know, so I'm actually going to call this x3 and v3. All right, there's two steps to this question. That's what's tricky about it. What was I not given that I need? Do you see anything in kilograms in that question? Okay, so I can't find out what its speed is at this position without mass. But they gave me the point of maximum amplitude, and they gave me information about the equilibrium position. So I can do this. Okay, so 1/2 Ka squared, I'm going to make that my initial energy, equals 1/2 mv max squared, just like the last question. But I know V, I know A, and I know K. The only thing I don't have is M. So I can solve it with the first bit of information they gave me, and then I can use it in the second part. Okay, do you want to try and solve it yourself?
Yeah, no,
before I do the rest?
I just missed the first one.
Okay, all right. Any others we need to go over, guys? 12? All right, so we got a vertical spring. K is 28 newtons per meter. Okay, object's displacement is 0.18 meters. Okay, what is its potential energy? Okay, so it's just asking me what's the potential energy at this point. Okay, it's not asking me about mechanical energy, it's just saying what's its potential energy. It's probably moving, probably has kinetic energy, but that's not what the question is. It's a trick. It's a wording trick, totally. Okay, all I have to do is punch in my numbers here and solve for EP. Okay. And then again, those are the dirty tricks that I play, right? Okay, any others? How many people are done? Okay. Keep working then, guys.